In this lecture, we'll be considering the normal distribution and the steps of hypothesis testing. This lecture introduces the normal distribution, highlighting its properties, symmetry, mean, median, and mode equality, and the empirical rule. It explains the standard normal distribution and z-scores, then contrasts parametric and non-parametric tests, noting how sample size affects test choice. The core of hypothesis testing is outlined. Formulating the null and alternative hypothesis, calculating test statistics and p-values, and making decisions using significance levels. It also covers type 1 and type 2 errors. We emphasize common misconceptions, for example, what the p-value actually means, and advice on choosing one-sided versus two-sided tests. The distribution and shape of a variable in a data set gives information about all the values the variable takes when the data are split into reasonably sized groups. It also gives us information about how often each value occurs. It tells us about the shape, center, and amount of variability in the data. Checking the distribution of the data is always one of the first steps of data analysis. Knowing the shape of the data provides insights into the data's statistical properties. There are some general shapes that occur so frequently in nature that these distributions are given their own names. The most well-known distribution has a shape similar to a bell and is called the normal distribution, or sometimes the bell curve, or Gaussian curve, or just the normal curve. The normal distribution is the most important probability distribution in statistics. Many natural phenomena, for example, height, blood pressure, measurement error, and IQ scores follow the normal distribution. The normal distribution has the following properties. It is symmetric, the mean, the median, and mode are all equal, and half of the population is less than the mean, and half is greater than the mean. These properties are true when the distribution is normal. The empirical rule allows us to determine the proportion of values that fall within certain distances from the mean. The empirical rule describes the percentage of the data that fall within specific numbers of standard deviations from the mean for the normal distribution. So within one standard deviation of the mean, on either side of the mean, we expect to find 68% of the data. If we look at the range of two standard deviations, plus or minus the mean, we will expect to find 95% of the data occurring within that range. If we extend to 3 standard deviations on either side of the mean, 99.7% of the data is going to fall within that range. The normal distribution has certain parameters which define its shape and its probabilities. The normal distribution has 2 parameters: the mean, represented by the Greek letter mu, and the standard deviation represented by the Greek letter sigma. The equation that we see on the right side of this slide is the equation for the normal distribution. And as we can see there, the mean mu and the standard deviation sigma are what give the normal distribution its shape. The shape of the normal distribution changes based on the parameter value. Thus, we compare these 2 normal distributions. They both have the same means, right? That's on the left side, we see the normal distribution for 2 different standard deviations. So the mean is the same, it's 100, but the standard deviation varies. So the blue curve has a standard deviation of 15, while the red dashed curve has a standard deviation of 30. And as you can see, that influences the pickedness or how tall the distribution is, albeit they both have the same mean. If we now look at, on the right side of the slide, we look at two normal distributions that have different means but the same standard deviation. We can see that they have similar shapes and heights. However, they are not concurrent. One of them has a higher mean than the other. So the dashed red distribution has a mean of 150 and the blue curve has a mean of 100. We look at the standard normal distribution. This is a special case of the normal distribution, and this is the distribution whereby the mean is 0 and the standard deviation is 1. This distribution is also known as the Z distribution. So it's known as the standard normal distribution or the Z distribution. It has a mean of 0 and a standard deviation of 1. What this helps us to do is that we can look at values on that standard normal distribution, and that value is known as a standard score or a Z-score. A standard score represents the number of standard deviations above or below the mean that a specific observation falls. So for example, a standard score of 1.5 indicates that the observation is 1.5 standard deviations above the mean. On the other hand, a negative score represents a value below the average. The mean has a Z-score of 0. Why? And so this is the formula that helps us to calculate the Z-score or the standard normal distribution score. So X represents the raw value of our measurement, mu is the population mean, and sigma is the population standard deviation. And so Z is given to us by X minus mu divided by sigma. Why is this important? Well, this is important because we can convert any normal distribution to the standard normal distribution. And thus, once we convert that, the X value is transformed into the Z-score, which tells us how far away in terms of standard deviation it is from the mean. Many statistical tests are based upon the assumption that the data are sampled from a normal distribution. These tests that use this assumption are known as parametric tests. The commonly used parametric tests that we encounter are the mean. We've been talking about that even before now. The standard deviation, the student t-test, the unpaired t-test, the paired t-test, ANOVA, analysis of variance, Pearson correlation, linear regression. These are commonly used parametric tests. They, however, also have non-parametric versions, and these non-parametric versions include the median, the interquartile range, the Wilcoxon test, the Mann-Whitney test, the Kruskal-Wallis test, the Spearman correlation, and non-parametric regression. Non-parametric tests are not based upon the assumption that the data are coming from a normal distribution, which means we can use them for distributions that are skewed or not normally distributed. What happens when we use a parametric test with data from a non-normally distributed population? Well, it depends. If the sample is large, the central limit theorem ensures that parametric tests work just as well with large samples, even if the population is not normally distributed. The exception to this is if the population distribution is really weird, in which case you're probably safe choosing a parametric test when there are at least 24 data points in each group. So if you have a large enough sample size, Based on the central limit theorem, even if the population is not normally distributed, you can use the parametric test. If the data is from a population that is not normally distributed, if the sample is large, you can still use the non-parametric test. However, you should note that when we use non-parametric tests for large samples from non-normally distributed populations, the p-values tend to be a bit larger than we expect. But the difference between the non-parametric test and the parametric test is a bit small. So in other words, non-parametric tests are only slightly less powerful than parametric tests with large samples. What if the sample were small? If the sample is small, then we can't use the parametric tests. We cannot rely on the central limit theorem. The p-values we get may be inaccurate. If we use a non-parametric test with data from a normal population, we run the risk of losing power. We may end up with p-values that are a bit on the high side. The non-parametric test lacks statistical power with small samples. We shall now consider some terms that we use in hypothesis testing. The null hypothesis is a statement that declares the observed difference is due to chance. It is the hypothesis the researcher hopes to reject. The alternative hypothesis is the opposite of the null hypothesis. It is the hypothesis the researcher hopes to bolster. Alpha is the probability the researcher is willing to take in falsely rejecting a true null hypothesis. The test statistic is the statistic we use to test the null hypothesis. The p-value, and this is a term we've come across quite frequently and often used in our conversations. The p-value is a probability statement that answers the question, if the null hypothesis were true, what is the probability of observing the current data or data that is more extreme than the current data? If the null hypothesis were true, what is the probability of observing the current data or data that is more extreme than the current data? The p-value is the probability of the data conditional on the truth of the null hypothesis. It is not the probability that the null hypothesis is true. Type 1 error. This occurs when we reject a true null hypothesis. In other words, we raise a false alarm, or it's a false positive. The type 2 error is when we retain an incorrect null hypothesis, so we fail to sound the alarm. It is a false negative. It is a false negative. So you can think of a type 1 error as crying wolf when there is no wolf. We all remember the story of the boy who cried wolf. And the type 2 error is failing to cry wolf when the wolf is actually there. And that's what happened in the story of the boy who cried wolf. When the wolf actually now came, the people failed to believe him. And so, the villagers committed a type 2 error. The confidence, and we've come across that term when we talk about confidence intervals. It is the complement of alpha. It is 1 minus alpha. Beta is the probability of a type 2 error. It is the probability of retaining a false null hypothesis. That is to say, the probability of failing to sound the alarm. Power is the complement of beta. It is the probability of avoiding a type 2 error. It is also the probability of rejecting a false null hypothesis. And here are the 4 steps of hypothesis testing. So when we come to testing hypothesis, this is essentially what we are doing. We have the first step where we determine the null and alternative hypothesis. Then we apply our test statistic and we select our p-value and come to a conclusion. And then the 4th step is we make our decision whether to reject the null hypothesis or not to reject the null hypothesis. So step 1, null and alternative hypothesis. The first step of hypothesis testing is to convert the research question into null and alternative hypothesis. Null hypothesis is a claim of no difference. The opposing hypothesis is the alternative hypothesis. The alternative hypothesis is a claim of a difference in the population. This is the hypothesis the researcher often hopes to bolster. It is important to keep in mind that the null and alternative hypothesis reference population values and not observed statistics. I repeat, it is important to keep in mind that the null and alternative hypothesis reference population values and not observed statistics. In the second step, we calculate a test statistic from the data. And there are different types of test statistics depending on the nature of the data, that is, the types of variables that we have observed, and the null and alternative hypothesis. The test statistic will compare the observed sample statistic to an expected population parameter. So, the test statistic compares the observed sample statistic to an expected population parameter. Large test statistics indicate that the data are far from expected, providing evidence against the null hypothesis and in favor of the alternative hypothesis. The type of test statistic we'll do will depend on the scale of measurement and whether we have just 2 groups or we're looking at 3 or more groups. So for example, looking at this table, if the scale of measurement was dichotomous or nominal and we're comparing 2 independent groups, we would do a chi-square test or a Fisher exact test. If for dichotomous or nominal variables on the scale of measurement, the groups are paired, matched, or correlated, we would do a Mach-Nemar test. So in this table, we see the different tests that we can use depending on the number of groups and depending on the scale of measurement. So we see the test for 2 groups and the test for 3 or more groups. So for example, if we had continuous or normal variables on the scale of measurement and we're looking at 2 groups for two independent groups, we do the t-test. If the 2 groups are related or paired or correlated, we do a pair t-test. And the equivalent test statistic for 3 or more groups is the ANOVA and the repeated measures ANOVA respectively. The third step. In the third step of hypothesis testing, the test statistic is converted to a conditional probability, which we call the p-value. It answers the question, if this null hypothesis were true, what is the probability of observing the current data or data that is more extreme? Small p-values provide evidence against the null hypothesis because they say the observed data are unlikely when the null hypothesis is true. We apply the following conventions. When the p-value is above 0.1, the observed difference is not significant. If it's below 0.1 but above 0.5, the observed difference is considered to be marginally significant. If it is below 0.5, 0.05, the observed difference is significant. If the p-value is below, less than or equal to 0.01, the observed difference is highly significant. Please note that use of significant in this context means the observed difference is not likely due to chance. It does not mean that that difference is important or meaningful. Statistical significance is not the same as clinical significance. So this is important to note. Should we go with a one-sided or a two-sided p-value? Well, you as the investigator must choose whether you wish to calculate a one- or two-sided p-value before you even collect any data. The p-value is calculated for the null hypothesis that the two population parameters are equal, and any discrepancy between the two sample statistics is due to chance. If this null hypothesis is true, the one-sided p-value is the probability that the two sample statistics will differ as much as was observed or further in the direction specified by the hypothesis just by chance, even though the means of the overall populations are actually equal. So, the one-sided p-value has a direction. This graph seeks to illustrate the concept. In the one-sided p-value, you can see that the red colored area, the rejection region, is all on one side or one tail of the probability distribution. And the threshold below which we reject the null hypothesis is known as the critical value. In contrast, we find that for a two-sided p-value, the rejection region is distributed in both tails, and the area is proportional to alpha over 2. So in other words, the probability of committing a type 1 error or of falsely rejecting the null hypothesis is distributed in the two tails of the normal distribution. So you can see it on this diagram here, where it shows the upper tail, alpha over 2 colored in red, and the lower tail, alpha over 2 also colored in red, and you have two critical values and two zones where we would reject the null hypothesis. A one-sided p-value is appropriate when you can state with certainty and before collecting any data that there will either be no difference between the means or that the difference will go in a direction you can specify in advance. That is, you have specified which group will have the larger mean. If you cannot specify the direction of any difference before collecting data, then a two-sided p-value is more appropriate. If in doubt, select a two-sided p-value. The fourth step is to make a decision. Alpha is the probability threshold for a decision. If the p-value is less than or equal to alpha, we will reject the null hypothesis. Otherwise, it will be retained for want of evidence. The type 1 error. Again, the chance of finding a difference when none exists. A type 1 error is the p-value, is our lack of confidence in the result. And this is what we refer to as a false positive. Again, remember my analogy with the boy who cried wolf. He cried wolf when there was no wolf. So that's a type 1 error. It was a false positive. The confidence level, 1 minus alpha, is the probability of a true difference. That is our confidence in our results. The type 2 error, represented by the Greek letter beta. This is the chance of finding no difference when there is indeed a difference. Beta. And this is called type 2 error. This is what we refer to as a false negative. Power is the complement of beta. It is the chance of finding a difference if there really is a difference. This table, 2 by 2 table, tries to help us illustrate what type 1 and type 2 errors are. So consider that in a courtroom, the judge has to arrive at a verdict. And the truth is that the defendant is innocent. If the judge renders a guilty verdict when in truth the defendant is innocent, the judge has committed a type 1 error. If the judge renders a not guilty verdict when in truth the defendant is guilty, then the judge has committed a type 2 error. There are certain fallacies that we come across in statistical hypothesis testing. And one of these fallacies is failure to reject the null hypothesis means that it has been accepted. That is not true. Failure to reject the null hypothesis just implies that we do not have enough evidence for us to reject the null hypothesis. Another fallacy is that the p-value is the probability that the null hypothesis is incorrect. That is not true. The p-value is the probability of observing the current data or data that is more extreme, assuming the null hypothesis is true. Alpha equals 0.05 is a standard with an objective basis. The truth is, look, that we set our p-value at 0.05 is merely a convention that has taken on unwise mechanical use. Truth is, there is no sharp distinction between significant and insignificant results. Only increasingly strong evidence as the p-value gets smaller. Another fallacy of statistical hypothesis testing is that when we find small p-values, they indicate large effects. That is wrong. P-values tell us nothing about the size of an effect. Another fallacy is that data show a theory to be true or false. Based on the modern empirical method, we cannot state that. Data can at best serve to bolster or refute a theory or a claim. Another fallacy is that statistical significance implies importance. Again, this is incorrect. Statistical significance says very little about the importance of a relation or association. According to John Tukey, a famous statistician, an approximate answer to the right question is worth a great deal more than a precise answer to the wrong question.